Okay, thank you for giving me the opportunity to talk today. And I'll just go over some of my research. Let's see here. So I have been at UCF for about 2 years now. Prior to that, I used to work at Lockheed Martin. I worked there for years, and as a matter of fact, before then, I was in Raytheon. So I'm currently an assistant professor in the Center for Research in Computer Vision, which is part of computer science. And so far, I've had the pleasure of teaching 2 courses. One is the Computer Vision Systems course, which is typically taught in the fall of every other year. And also I've taught the Computer Vision course once just this past fall, which is more of the first graduate course in computer vision. My research has been mostly funded by the DoD so far. There's a couple of different projects that are coming in from DARPA, the U.S. Army, and some from industry, also from the DoD side, and they're listed over here. And so far, I've just gotten, being here for 2 years, gotten the research team together and some funding in place, and just beginning to crank the machine on getting publications going. But just in a nutshell, I'm tremendously enjoying the experience of coming back into academia after many, many years in industry, but it's like learning a whole set of new skills, right? So the next chart is actually why I came back into academia. Of course, in the industry is always focused on getting things to market. There's a lot of advanced engineering, as you can imagine, but sometimes it's much more application oriented and leaves less time for fundamental research, and so that has always been my motivation for getting back into academia. And my focus is more on imaging modalities that are not the usual type of imaging that goes in computer vision. It has more to do with the kinds of imaging modalities that you encounter in the aerospace industry or the DoD in particular, but also, satellite imaging, remote sensing, they all have similar sensors. And the goal is really to see things from very far away under very challenging conditions, things that are small, things that don't really show up in the usual RGB images. And of course, my goal in doing some of this is to train our graduate folks, graduate students, with an emphasis on real-world problem solving. Part of it coming from industry, my perspective has been that we have to train talent in advanced research for our industries and for the government labs. And so from part of that perspective, I've been working with Mubarak Shah and Niels Lobo to try and see if we can offer some of our computer vision courses at local industries, starting with Lockheed. Some of that is going on, but of course, COVID-19 has put a twist on all of that at the moment. I'm going to just quickly give you an overview of, a couple of research things that are going on. I'm, in the interest of time, kind of keeping it at a very high level, but we can always discuss things in more detail if somebody's interested. This one is a project that I got last year from DARPA, and to be absolutely honest with you, I was very surprised that I got it because it says it's a young faculty award, and I'm not young by any means. But if I'm young, it's good news for many of us, I think. That said, the idea is basically that computer vision algorithms tend to process things with the same computational complexity. And the goal of this project was to sort of say that humans, on the other hand, when we do a certain task over and over again, we become specialists at it. So if the task occurs frequently, then we tend to do it much more quickly, with less thought, with less time. Whereas if something new or rare happens, then of course we have to think about it and take more time for this rare task. On the other hand, in computer vision, most algorithms work with the same computing complexity, regardless of how frequently the event occurs or how rare it is. And so from that point of view, I and my students are, my student is Sashank Venkatramanan. We are working on a knowledge distillation framework where a much lighter, there is a more complex high-capacity teacher network that has all the knowledge that the task needs to be performed with. But for the frequently occurring tasks, a lighter binary student network rapidly learns, if you will, the prior probabilities of the frequently occurring classes. And in the process, it performs those tasks with much less computing complexity and much more quickly. And to do that, we have to look at the underlying data manifold and make sure that we are not only learning the frequently occurring classes, but also have the ability to detect an event when something new or something rare has happened. So it has to also take into account the need to avoid catastrophic failure and things like that. This is just a little bit showing there's a tremendous reduction in the computational complexity, as well as the while very little is lost in the performance. The next one, which is also related to the same project, was with another graduate student of mine, Mohammed Tayyab. He is looking at it from the point of view of network compression. There is tremendous redundancy in deep learning networks, as we all know. And there is a lot of work out there that has been done on compressing networks, filter pruning, low rank reductions, and so on and so forth. But again, coming from a more applied perspective, these algorithms for optimizing and compressing networks are very effective, but they do require special purpose optimization algorithms. They're not necessarily available in the conventional toolkits. And so our goal was to come up with something that's very simple. It's a different way of looking at the convolution kernels. We're looking at it more from a signal processing, call it basis representation perspective, where the fine-tuning of the algorithms happens in a spectral domain. So it's like a spectral decomposition of the filters. And then instead of updating or fine-tuning the filters in the spatial domain, which is where most of the work happens, we look at it as optimizing the spectra of the filters in a transform domain. And it turns out that reduces a lot of the parameters, but also these plots are showing that for different networks and different data sets, I'll just point this out very quickly. Compression may reduce the performance drastically, but the optimization in the spectral domain reduces and restores it back again. So we have seen this over and over again. This is a paper that's under review right now in PAMI. We'll keep our fingers crossed. The next one has to do with detecting targets in the infrared imagery, both moving targets and stationary targets. And this is being funded by the U.S. Army, Night Vision Lab, and Leonardo DRS. And the goal here is that, so much work in object detection and classification in computer vision. A lot of networks exist, Faster RCNN, YOLO. There is something called Detectron you all know about these state-of-the-art methods. But when we go to apply them in the infrared domain, they don't work as advertised. I shouldn't say that. They don't work as dramatically as they do on RGB images. And there's numerous reasons for that. It's the fact that they were trained for RGB. There is not nearly the kind of millions of training images in the defense and aerospace business that there is in the, let's call it the commercial world. The nature of the data is different. The targets are much farther. They're much smaller. The clutter is much more difficult, and so on and so forth. So long story short, we have been defining performance metrics that are relevant for the problem from a DoD detection point of view. So instead of defining cross entropy or mean square error losses, we have defined new metrics like target to clutter ratio, things that are more indicative of the infrared phenomenology, and directly optimized our algorithms for that. And there has been obviously corresponding improvement in the performance, and we're trying to move, inspired by what's been going on in computer vision, find analogous that bring about similar gains in the DoD applications. So that said, over the next 2 years, I'm hoping, so as you've noticed, that my funding comes more from the DoD side and from the industry side. I'm very much interested in pursuing funding from NSF that will allow us to do more fundamental work in machine learning and machine vision. And also, instead of working on algorithms just as an afterthought, I also have worked in the past in something called computational imaging. So we're trying to move the algorithms closer to the sensors, to move them more upstream so that they're more directly part of, in fact, the sensing process itself. And if there's applications of machine vision in manufacturing, material science, automation, self-driving cars, I'd be very interested in collaborations in those areas, and also still in the process of setting up demonstrations and test beds using infrared cameras. I'm working with Mubarak and Yogesh as we speak, and perhaps securing some DURIC funding and so on. And finally, over the next 4 or 5 years, my goal is hopefully to contribute to the expansion and recognition of our center, outreach to the community, CRCV in general, work with local industry. And so that's something that I would be very much looking forward to lending a hand in as we go and work with the local shareholders and local stakeholders to extend the role we can play both in a technology sense and an education sense. And with that, I'd like to acknowledge my graduate students and undergraduate students who are in the group right now. And I reach out to a lot of people in the department. I can't list all of them all the time for help, without whom this would be very difficult to do. So with that, I'd like to hand it back to you.
Very good.